So, on a side note, so I first introduce myself. My name is Zach Conti, associate at the Turing Institute in London here. And for those of you who are not familiar with the institute, Turing, as we call it, is UK's National Institute for Data Science and AI. And I also like to introduce the co-organizers of the seminar. So there is David, who is in physical form today, and David is a PhD enrichment student here at the Turing, and there's also Andrea Pisaperato. And Andrea Pisaperato is also a Turing fellow here in London. So on a side note, if any of you in the audience are interested in sharing your work within the stream, of course, then please, of course, feel free to get in touch with us, and we'll be happy to find a suitable date for a seminar. And I'd just like to say that we've kind of almost reached 300 subscribers, so it's becoming a nice platform for this growing topic. Right. The last thing I'll say is, if you would like to ask questions and answers, please save them for the end of the talk. We will allow around 15 to 10 minutes, which we can do when that time comes. So, without further ado, I would like to introduce Oliver, who is our today's speaker, and I'll ask David to introduce him. And thanks for listening.
Yeah, hello everyone. It's good to be here in person today. And also, yeah, thank you very much, Oliver, for getting to present today. I'm just going to give a brief introduction before you can start. So basically, for all of you to know Oliver, he's an assistant professor in cyber physical simulation within the department of mechanical engineering in the Technical University of Darmstadt. And before that, from 2015 to 2019, he was also a postdoc and an assistant professor at the Digital Manufacturing and Design Center at the Singapore University of Technology and Design. He got his master's degree in technomathematics from the University of Munich in 2011, and also his PhD after that in the Kaiserslautern Technical University in 2015. Yeah. So Oliver's expertise and interests lie broadly in the fields of computational mechanics and engineering. In particularly, his aim is to develop more efficient computational methods and implement algorithms that facilitate the integration of digital design, simulation, optimization, and manufacturing processes. And Oliver, the floor is yours. No.
Yeah, thank you very much for the invitation to give a seminar here today to Zach, Andrea, Daniel. It's my pleasure to introduce our work on multiphysics, material modeling, and multiscale simulation using physics-enhanced neural networks. And I did not do all this myself. Basically, within my group, there is Dominic Klein, who is a PhD student, Mauricio Fernandez as a former postdoc, and Till Gärtner as a former master student. And then we have plenty of collaborators also from within Germany and some also from Spain who contributed to the things that I will show you today. So the outline for my talk looks as follows. I'd like to start with a short introduction of the work that we do at my group in Darmstadt in general, and a motivation of the work that we'll be seeing today, which is mainly the usage or the development of physics-enhanced neural network constitutive models, material models for applications in hyperelasticity and in the multiphysics context, also in electroelasticity. After I've presented these developments to you, I'll finish with a short summary and outlook. So as already mentioned in the introduction, basically the research that I'm interested in and that we do in my group is basically trying to connect physical and data-driven modeling concepts, such as physics-enhanced neural networks, with the development of advanced numerical methods and the connection to advanced manufacturing technologies such as 3D printing, or also 3D knitting, which we did a lot in Singapore. So basically, here you see a lot of topics that we are working on. I will not discuss all of them in detail, but today basically we are looking into physics enhanced machine learning in application to continuum and multiscale mechanical and multiphysical modeling, which is also connected to numerical methods in terms of homogenization and multiscale simulation, and to applications that I will show, which can be connected to metamaterials and to lattice structures in the context of 3D printing. And here's a picture of some of the people working on these topics. Basically, this is a view from our terrace in our office onto the so-called Odenwald, which is a nice middle mountain area close to Darmstadt. So the motivation of this work is in general that in the last years and maybe 1 to 2 decades, there have been a lot of developments on advanced manufacturing technologies and advanced materials technologies that enable the fabrication of components with multifunctional properties and capabilities, which are also tailorable at various length scales. Meaning that, for instance, we have additive manufacturing, 3D printing, where we can manufacture and design metamaterials and lattice structures that show interesting effects like buckling, which can also be exploited, that are tailorable in terms of, for instance, the mechanical response, like you would see here in such a shoe midsole, and also other interesting materials like electroactive polymers, which you see over here, which can change or introduce a shape change when an electrical field is applied to a material, or textiles, where you see an example where a grading is applied, where 2 different kinds of knitting patterns are combined in this material. Of course, also, let's say, more traditional composites, where you have multiple phases or fibers that can be distributed in a matrix material in different fashions, like different kinds of orientations or random distributions, and so on. And then also biomedical applications like additively manufactured prostheses, for instance, or also biomaterials or biological materials like tissues and muscle materials and so on. And what all these examples have in common is that they yield various challenges on the side of modeling and simulation, which is, first of all, the question is always whether we have a so-called scale separation, which would allow to regard the structure as a continuum on the macro scale and then kind of zoom into the smaller scale. If this scale separation is not really given, then we have to do a full-scale simulation. For instance, for this shoe sole, if you want to model this, you really have to discretize all the elements of this lattice structure to model it accurately. Then the question is also, do we or can we stick to linear modeling, or do we have to use nonlinear models, meaning that there can be large deformations or instabilities which require nonlinear mechanical approaches. The material behavior can be also nonlinear, can be isotropic, can be inelastic, which means there is dissipation because of plasticity or viscoelasticity or other inelastic effects, growth effects, or multiphysical behavior, like for instance for the electroactive polymer, where you have a combination of mechanical and electrical fields that influence the response. Then in many of these technologies, also uncertainties and tolerances play an important role, which should be considered in the modeling. If we have this scale separation, there can still be certain kind of size and localization effects. And ultimately, like already mentioned, if we have the capability to grade the material or to locally change how it looks like, then we ideally want to optimize it so that we get the best material distribution for a certain purpose. So we try to address all of these challenges more or less. And here I just want to show some results, basically, where we do not do a multiscale modeling and where we do not use physics-enhanced neural networks, but where we basically developed a workflow to simulate lattice structures. We did this a few years ago when I was still in Singapore, where we just look at elastic behavior. And then very recently, we also extended this modeling of lattice structures using efficient beam elements to inelastic behavior, which means that basically we can simulate the compression of such a lattice structure even under the influence of instabilities, which you would see here in the kink of the curve, the compaction where contacts occur, and then also a combination of plasticity and viscoelasticity occurs. And this can be modeled here at the full scale. However, if we have a structure where scale separation applies, so basically where we can look at the structure as a continuum at the macro scale, so we do not really see that it has a microstructure, but if we zoom in, then basically we see the microstructure, and this is typically modeled in terms of a so-called unit cell or representative volume element of the microstructure, which you would see here for such a specific kind of beam lattice. So in this case, we want to do a multi-scale simulation where basically the idea is that if we have a continuum, we can take the deformation or the strain there here in terms of the deformation gradient F and prolongate that to the microstructure, which means that the averaged effective deformation of the microstructure should be equal to the deformation that we have specified at this point. And this can be enforced, for instance, using boundary conditions. And this would lead to this deformation of the microstructure. You see it in the picture. There you have a deformation, so you also have a stress. And now here, the first pillar curve of stress P is averaged over this microstructure, this deformed microstructure, and then this is transferred back to the macro scale. And then we say now the stress at this point is equal to this average. And this can be done, or this makes sense, because basically in this way we ensure that the internal energy or the variation of the work or energy on the macro and on the micro scale are equal. So with this homogenization, basically we obtain an effective stress-strain relationship of the microstructure. Now we can do finite element simulation on the macro scale, but basically we do this prolongation and homogenization hence and forth for every point in the macroscopic continuum. This is called a concurrent multiscale simulation or FE squared method, but this is computationally very expensive. So ideally what we want is we want an effective constitutive model, an effective material model that just gives us the stress for a given strain or for a given deformation. So this means basically we look at this microstructure as if it really was a normal material. And this can be challenging. So in our case, in this presentation, we will always use physics-enhanced neural networks in order to represent such a constitutive model, which we can then use in a normal finite element simulation where we look at this as a continuum. So this is the goal of this work, basically to apply this workflow, homogenization of the microstructure, formulation of a constitutive model, and then using this model for a macroscopic finite element simulation. Now, for these kind of beam structures that you saw in the previous slides, basically, we model the unit cells using 3D beam elements, which can consider finite deformation and rotations. And for now, we focus on linear or an elastic material behavior, where you see here, for instance, an example of a BCC lattice unit cell, where we apply also some stiffening at the nodes, which basically is more physical than when you would just have the straight beams. And then you see the structure in its initial shape, and then under different kinds of boundary conditions for uniaxial compression, uniaxial for planar compression, and so on and so forth. And here, like you saw on the previous slide, basically we have this so-called Hill-Mundell condition, which says that the effective strain and the effective stress should be connected to the average stress of the microstructure in such a way that the energy on both levels on the macro and the micro scales is the same. Now, in order to generate data, so this is the first step in this multi-scale framework that you saw on the previous slide. Basically, here we apply macroscopic load cases like uniaxial tension and compression, a combination of shear and tension and so on, and then evaluate the internal energy W and the first Kirchhoff stress P, or the effective quantities of those for these deformations. So basically then we get this kind of strain stress plot where we have here the strain ranging from -30% to +30% for this uniaxial tension case, and we plot the stress where these curves would be the main tensile stress component. And we can do this for different kinds of scenarios, and in this way we generate data, stress strain data for this given microstructure. Here, since we have instabilities, we need to take care also of the post-buckling behavior and apply some perturbation methods in order to make these simulations. But basically what you see in these curves is that these kind of microstructures, they show a highly nonlinear behavior. So here, because of the instability, you have the kink in the compressive behavior, and you also have some sort of kink here or here in shear behavior, which makes it very difficult to find a constitutive model that can represent this behavior. So the next step, like I said, is to try to find a constitutive model and material model that can represent this behavior. So we focus on elastic behavior, which means that the deformation is recoverable, and we apply the concept of hyperelasticity, which is, say, the default of modeling elastic material behavior in continuum mechanics. And hyperelasticity means that we assume that a so-called strain energy function or stored energy function W exists as a function of the deformation gradient. And when we take the derivative of this function with respect to the deformation gradient, we get the stress here in terms of the first Kirchhoff stress tensor. And when we do that, basically we automatically ensure energy conservation, which would require that the rate of the change of the strain energy is equal to the product of the stress and the deformation gradient. My dogs are making some noise. Give me a second. Sorry for this interruption. I'm back now. Yeah, where did I stop? Basically here we have energy conservation. And now this strain energy function or stored energy function, it has to fulfill a lot of requirements due to physical and mathematical considerations. So first of all, it should always be non-negative. And if we have the identity as an input, which means we have no deformation, no strain, then we should also have no energy. Then there is material frame indifference, which means that we have that we can rotate the coordinate system in any arbitrary way, and we see that and this should not make no change to the energy. Then we have the material symmetry, which should be considered. So when there are certain changes of the orientation of the material should still behave in the same way. So basically, if you have an anisotropic material, you can rotate the material in any way and you still get the same result. Then you have certain growth conditions that must apply. So if you have infinite compression or infinite tension, your energy should go to infinity. And then also importantly, there should be material stability, which is ensured by the ellipticity condition, which means basically that this expression over here, which is very difficult to verify, should hold, which is why people came up with the concept of polyconvexity, meaning that when you formulate the W as a function in terms of f, the cofactor of f and the determinant of f, it should be convex in all the arguments. So basically this function, the second derivative of this function, should be positive semi-definite, which we see over here. And this condition is easier to ensure than this condition, which is why when constitutive models are formulated, typically we try to make them polyconvex. So analytical models, analytical constitutive models are typically formulated in terms of invariance of the right Cauchy-Green tensor C, which is F transpose F. And in this way, many of the requirements can be ensured. However, if you want to find or formulate a new material model, this is tedious, and then also you need to have a way to fit it. So for instance, ANSYS or similar CAE software, they also have tools which help you to fit material models. However, if we have such very high linear, nonlinear data, basically analytical models are not flexible enough to describe this stress-strain relationship, especially for anisotropic materials, anisotropic metamaterials, where the library of material models that we have is not as big as for isotropic materials. Somebody wants to say something?
Sorry, Oliver, the problem is that I only see slide 4 now, and it's still for a while now. I didn't see anything changing.
Oh.
I can see, I'm on slide 9 now.
I mean, sometimes it depends on the browser. Some people who are working with some other browser like Chrome, it has to pause something. Are you using the Zoom app?
No, I'm using the Chrome client directly through Chrome.
That was my assumption.
Okay, but those who are using the
again, because Oliver, sorry, you just talked and I was like, but I don't see the equations. I don't see anything. So okay, I'll just do it again.
Yeah, if you don't
can watch the video afterwards, hopefully.
Yeah.
But all the other people that are using the Zoom app, they can see slide 9 now, right?
That's correct.
Okay, so I just continue. Okay, so basically what we want to do now is we want to use artificial neural networks, feed-forward neural networks, because they have universal approximation capabilities, which means they should be able to represent any kind of complex nonlinear function in order to formulate such a material model, or in order to express such a strain energy function F. But we want to enhance the neural network model, the model formulation, with the physical requirements that hopefully most of you saw on the previous slide. So basically, our first attempt at this, and we are not the only ones who have been having this idea, many other people have done it before, but basically we try to do it in a way that really incorporates as much as possible all the requirements that you saw on the previous slide. So we formulate a strain energy function W in terms of the right Cauchy-Green tensor C, which is subject to this kind of weird sum symmetrization operation. And why we do this, I will explain in a minute. So we will say, and then this W naught over here, this would actually be the neural network. We do this kind of weird architecture because we want to enhance the model with the physical and the mathematical requirements. So in general, if you want to introduce physical information and requirements, if you want to introduce a so-called inductive bias from physical requirements into machine learning, it will greatly improve the model generalizability and also in many cases the accuracy. So when I say enhance, I basically mean essentially two things, which can be either informing the model or augmenting the model. And I'll explain in a minute what I mean by these terms in terms of the physical information. And this can be done either in a soft way or in a hard way. I'll also explain what I mean by that. And these concepts, basically, they were defined in this paper that you see on the top over here. So physics informed in the definition of this paper, and I kind of agree with it, is when you have a so-called discriminator that can measure the violation of a physical property or a physical requirement. So let's say you have a partial differential equation, you substitute a potential solution function into the equation, and then it is not exactly a solution, so there will be some residual, and you can measure the violation of the PDE in terms of this residual. So you have a discriminator, which would be measuring this violation. So this is essentially done in physics-informed machine learning or in physics-informed neural networks, where the violation is typically included into the loss function of the neural network learning procedure by some penalty terms. And this means that the fulfillment of the physical requirement in this case is only approximated, so we only have a soft fulfillment of the requirement. Because the minimization of the loss function, it may not lead to the physical requirement being fulfilled for all possible inputs in a guaranteed fashion. In contrast to that, by physics, for physics augmented machine learning, you need a so-called generator, which is some function or functional that can generate objects that automatically possess the desired physical property. So this, explain this again in more detail in a minute, is the usage of invariants which are automatically objective in the formulation of a constitutive model. So in physics augmented neural networks, we change the model architecture, or we enhance the model architecture using such generators, which make sure that the physical requirement is fulfilled in a hard fashion. So by construction, we always get a result that fulfills this physical requirement. And then depending on the context, you can also think of other ways how you can inform or enhance the model with physical requirements. Constraints would also be possible, but this is a bit difficult to implement with the optimizers that we typically have when we train neural networks. And data augmentation is a concept that we will also use and that I'll show in a minute. So having said all that, I come back to this model formulation over here. So here I put these gray stars, which means that all of these things are generators in the sense of physics augmented machine learning. So basically by formulating a material model, which ultimately is supposed to give me the stress P as a function of the deformation gradient F, by formulating this model as a hyperelastic model using a strain energy function, I automatically fulfill thermodynamic consistency. By using C as an input instead of F, I am automatically objective. So this is a generator for objectivity. And using this symmetrization approach over here, where we sum over all elements in the symmetry group of the material, we automatically fulfill the desired material symmetry. So basically now we have a hyperelastic model that is objective, anisotropic, that has a high flexibility because of this neural network that is used here, which basically takes the 6 components of C as an input and gives us as an output the scalar strain energy value. I fulfilled most of the requirements that you saw on the previous slide, but not the ellipticity requirement that we had. And we need this function W to be twice continuously differentiable. It needs to be once continuously differentiable because we are always interested in the stress. And then in a finite element implementation, we also need the elasticity tensor, which is the second derivative. But this is easy to fulfill just by the right choice of activation functions. So you use something like soft plus or tangent hyperbolicus or sigmoid, which is at least, or which are at least 2 times continuously differentiable functions. Now we also want to formulate models that are polyconvex, and therefore we use the so-called input convex neural networks. So these input convex neural networks were introduced in this paper, and basically you can make a neural network, feed-forward neural network convex in terms of its inputs by using convex and non-decreasing activation functions, such as the soft plus function, and by making sure that all weights are non-negative. So basically, we can formulate a polyconvex neural network-based material model by, for instance, using invariants. You see the definition of the invariants over here, which ensure objectivity and which can also ensure the correct material anisotropy, material symmetry, and just inputting these invariants into an input convex neural network that gives us the strain energy and then taking the derivative. So basically in this way, we have a hyperelastic, objective, anisotropic, polyconvex model that is very flexible because we use a neural network inside, but we lose some flexibility because we use these invariants, which may not be sufficient to describe all of the possible material behaviors. And here we also enforce the growth conditions using this analytical term, which just gives us this desired behavior for the determination of determinant of f going to infinity and going to 0. Then we also had another idea where we directly use the deformation gradient and the symmetrization operation that you saw on the previous slide. So now basically our strain energy function is given in terms of this input convex neural network P of f, which takes as an input actually 19 coefficients, which are f, the cofactor of f, and the determinant of f. We have the symmetrization operation and this analytical growth condition operation. Here we ensure all of the desired requirements except for the objectivity, because basically with this formulation in terms of f, it's impossible to directly enforce the objectivity condition. So here we resort to now a weak or a soft fulfillment of objectivity by using data augmentation. So basically we have our data set, which we use for the training, which contains deformation gradients and the corresponding strain energies and stresses. And now we use certain rotations. Ideally, we would have to use all infinite rotations that are in the group SO3, but we can only use a finite number. And basically, we rotate all the data with these rotations and enhance our data set. And then we hope by showing the model these additional inputs, it will learn the objectivity requirement by itself and approximate it in a more or less accurate way. So now let's come to the application of these models. So we start with this feed-forward neural network-based model WC. We train this model on, like I said, a training data set that contains for certain deformation gradients, the energy and the stress. This kind of training is called by some authors a Sobolev training, because our neural network should give us the function W, but we also provide information about the gradient, which is the stress. So this can be thought of similar to a Sobolev norm, where you have the function and the gradient of the function in the norm. So we find the hyperparameters of the neural network by implementing all of this in TensorFlow and training it to certain data, like I showed earlier, where we include uniaxial tension, biaxial tension, and so on in the training cases. And then we generated some test cases which combine all sorts of deformations. For instance, in this bottom case over here, you have a combination of tension and shear behavior. And what you see over here is basically the results of the stress strain curves that we get from the trained model here with only 2 hidden layers with 16 nodes each, where basically we see a very good agreement of the continuous lines, which are the data, and the dashed lines, which are the model predictions. So with relatively small architectures, we get here a good accuracy in predicting the stress-strain relationship. However, now if we check the ellipticity condition, it's quite surprising to see, and this can only be done numerically, that we have a violation of this ellipticity condition, even here, for instance, in this uniaxial tension case, where the data and also the model looks very good. So what this violation of ellipticity means is that basically here you see the deformation component F11, and now the derivative of the stress with respect to other directions, it must be somehow weird, so that overall the second derivative is not positive definite at these points. And this happens here in this uniaxial case, but also in other cases where the range where the model is elliptic is actually quite limited. So this suggests that we might need this polyconvex model to obtain stable finite element simulations. Now, if we use an analytical invariant-based polyconvex model, we are not even able to approximate just uniaxial tension in a sufficiently accurate manner, because the behavior is just too kind of strange that these microstructures have. now we train our invariant-based input convex neural network model on this data. And it also doesn't look very good, especially here in the share case where the model prediction, which are the continuous curves, are quite far from the data, which are it's indicated by the dots over here. And this might be the case because we have here a microstructure with a cubic material symmetry. And for cubic material symmetries, it is not clear actually how many and what invariants we have to use in order to describe the model. So the last resort now is basically this input convex neural network model WF, where we use directly the deformation gradient. But for this model, we cannot have objectivity in a hard-coded way, or hard implemented way, so we use the data augmentation. So that means basically now we have our data, for instance, of uniaxial tension. We choose 8 rotation matrices, 8 other observers with which we enhance the data set, and then we train the model on this data. And what you see in this plot here is now the evaluation of the model for a total of 1,000 randomly chosen observers, and the lines basically indicate the worst case predictions. So you see, if I use only 8 observers, I have a model that does not predict or does not capture the objectivity at all. However, if I increase the numbers of observers for my data augmentation, now with 64, I can hardly distinguish the lines of the worst cases anymore and have a very good approximation of objectivity. And now if we fit this model to the data, we get an excellent agreement. So here, basically, you see uniaxial and share cases, which were part of the training data set. And here, this biaxial test and the mixed test case, which were not part of the training set. And we have a very good prediction of the stress strain behavior in all cases. Now, and we get this even when we use only 2 cases, such as uniaxial tension and share, which are very simple training cases, to train the model, and we are still able to basically generalize the prediction of any other kind of deformation. So it's this convexity that we added here to the physics enhanced neural network gives us a physically and mathematically sound model, which is highly accurate and has excellent generalization capabilities. Now, if we go to a little simpler material behavior, here we have transverse isotropy, where we generate data from an analytical model. Then we fit the invariant-based neural network model, which here now we know which invariants exactly to use. Then here we get an excellent prediction or excellent fit of the data with a neural network that has just 1 layer and 8 nodes inside the layer. For the WF model, the prediction is not as good, and we need a much bigger network now, because here for transverse isotropy, we know which invariants we have to use, but the symmetry group for the material anisotropy is an infinite group. So basically here we need to approximate the symmetrization operation, for which we use only 6 rotations over here, and also the objectivity, for which we use 128 rotations over here, in order to get a more or less good fit. So we need to do a lot of data augmentation for this model for it to work well. However, then now we can use these models in multiscale simulations. So remember, we fitted the model to the behavior of such a lattice microstructure. Now we simulate such lattices using a full-scale simulation where everything is discretized using beam elements here in some sort of tension and compression cases. And we compare now this against the multiscale simulation where we use the material models with physics-enhanced neural networks. And you see here that there's a good agreement of the full-scale and the multiscale simulation. For larger strains, it diverges here a little bit, which can have multiple reasons. Can be because the constitutive model is not accurate, but can also be because of boundary effects that happen in the simulation. But we see here also basically that the simulation in compression with the WC model, which is not polyconvex, not elliptic, it terminates at some point, whereas for the WF model, which is polyconvex, you can simulate much more compression. And we were not the only ones who worked on this topic. So basically in Jabal Farhad's group in Stanford, they developed a very similar model, and they did a very good job in implementing it into a finite element simulation and showing interesting results where they show the dynamic vibration behavior of such a membrane, where the hyperelastic neural network and the convex hyperelastic neural network are much more accurate and much more stable than a simple regression neural network. And then they also showed that these kind of material models, they can be used very well also in fluid structure interaction simulations, for instance. So the physics-enhanced input-convex neural network gives a superior accuracy to completely uninformed neural networks in terms of accuracy and stability. Now, when we are looking into metamaterials or microstructured materials, we typically have families of microstructures, meaning that you could have a fiber reinforced material where you're able to change the volume fraction of the fiber content, or where you're able to change the orientations, or you have a foam where you're able to change the volume fraction of the foam or the pore size and these kind of things. So what you want is a material model that is parameterized in terms of these design variables of the microstructure. And here we apply this now to these beam-like microstructures, where we basically combine three different topologies. The orange one with struts on the edges, the green one with struts on the faces, and the yellow one with struts going through the center of the cell. And we scale now the diameter or the radius of these three topologies using a certain parameter. So basically we have three design parameters. If all radii or all diameters were 0, then we would not have any structure. But if one of them is non-zero, then we have a certain microstructure. And for this now, basically we have to sample the space of deformations, but we also have to sample the space of design parameters. And here, basically, we use a sampling strategy for this unit cube of design parameters, where we choose some regular points on the boundary of the parameter space, combined with a Latin hypercube sampling of the interior of the parameter space. Because we found that it's very important to have points on the boundary, which means that you really always interpolate in your design space. And we formulate now here a model in terms of the neural network based on the right Cauchy green tensor and the parameters. So we did this before we developed the convex model, which is why we did not use the convex model over here. Now, when we look at the mechanical behavior of these microstructures with the different parameters, we see that their mechanical behavior can be very different. So basically here I have a microstructure where the parameters are close to 1, which means that all the struts are very thick. So I have a stiff response. I get very high stress values here going up to 4,000. Whereas of course, when I make the struts thinner, I get a softer behavior. So here I have stress values up to 80. So we have like 2 orders of magnitude difference in the values that we're trying to fit with our neural network. So for that, it's very important that you introduce a proper weighting into these different cases that you're trying to approximate. And we found here that a very good solution is basically to compute the L2 norm, or a discrete approximation of the L2 norm, basically of these stresses integrated over the whole deformation range. And then you weigh basically by these L2 norms. And then when we do that, we get a very good fit. So these curves already show the data in dashed lines and the model prediction of our parameterized model in continuous lines, and you can hardly distinguish them, even though they have very different scales. Now, if we have such a parameter-dependent model, we can use it for optimization. So basically, we can say we want to have a desired response behavior, a desired stress-strain curve. Now, please find us the corresponding parameters. So basically, we use the nonlinear optimization for these 3 design parameters on top of the constitutive model in order to get the parameters that would give us a certain behavior. This worked quite well, but as I said, we did not combine this here with the polyconvex model. And this is not 100% straightforward, because basically you have this convex dependency on the deformation gradient, which you would need in your model, but the dependency on the parameters, it might not necessarily be convex. So basically, we will have to combine different network architectures that can take into account convexity with respect to some inputs, but not all of the inputs. Okay, then the last extension of this model that I want to show basically is going to multiphysics, in this case to electroelasticity. So for instance, for modeling electroactive polymers, you have this interaction between electric and mechanical behavior. And luckily, the mathematical structure of these problems is very similar to the case of hyperelasticity. So basically here, we need to find, in order to model the material behavior, so-called internal energy density function E, which now needs to be a convex function in terms of the mechanical deformation gradient, the cofactor, and the determinant, as well as the electric displacement field and some combination or rotation of the electric displacement field. And then we can get the the stress as the derivative of this internal energy function with respect to F, like we had it before, and we can get the electric field as the derivative of this function with respect to the electric displacement field. So the idea now is to, again, just use an input convex neural network in order to represent this internal energy, where now we use invariants as inputs, which makes life a bit simpler because we only have like 5 or a few more invariants depending on the symmetry group. And then this term is just this additional analytical term that ensures the growth conditions. So our model architecture, you see it up here, basically. We have the deformation gradient, we have the electric displacement field vector. With these, we generate also the cofactor and these combined invariants, these combined variables, and then from that we compute the invariants, and then the invariants are the inputs for the input convex neural network. The output is the internal energy, and we get the stress and the electric field just by differentiating that, which can be done easily in TensorFlow or any other neural network library. Now, in the interest of time, maybe I just skip this part and I come to some more interesting examples. So basically, we applied this now also to an analytically homogenized rank 1 laminate, basically, where we have 2 layers of materials with different material behaviors, which result in a transversely isotropic overhaul behavior. So we take the transversely isotropic invariants, generate some data, fit the model, and here you see a visualization of some test cases where this would be the applied deformation gradient and the resulting stresses, and the applied electric displacement field and the resulting electric field, where again the data would be the dots and the curves, the continuous lines would be the model prediction, and we get a very good accuracy here for this physics enhanced neural network model. Same thing also for the case of a metamaterial, which we homogenized numerically, which results in a cubic material symmetry, cubic material behavior, where again we apply some complex combination of deformation and electric displacement field to evaluate the model, and we get a very good agreement of the behavior of the microstructure and the prediction of the effective behavior that we get from the neural network. Now, finally, we are currently in the process of implementing this into nonlinear finite element simulations, where our collaborator from Cartagena, Rogelio Ortigosa, already has some results, but we haven't submitted a manuscript about this yet. So for what I'm going to show next, basically, we just use a simple isotropic strain energy function with isochoric invariants to generate data. We fit the neural network model to this data, and then we implement this in a finite element simulation and compare the finite element simulation with the analytical model versus the finite element simulation with the neural network-based model. So here you see 2 cases where we have purely mechanical behavior. One case where you have a beam that is bending, and the other case, a very strong twisting of a column. And if you look at just the comparison of the deformations and of the stresses that are visualized here in terms of the colors, you see that they are very, very similar. So this means basically that we have no convergence issues, and we get accurate results here for these mechanical cases. So these are all nonlinear, highly nonlinear computations. So we use a Newton-Raphson method to solve the nonlinear finite element problem. And in order for that, we must get the second derivative. We must get the elasticity tensor. And this seems to also be accurate, because otherwise we wouldn't get these results. Now, if we look at a combination of electric and mechanical behavior, here basically we have a gradient of the electric field throughout the height of this very thin membrane. And this gradient in the electric field, it introduces bending. And this is just a comparison of two different electric fields, here medium and here large, where you see again the comparison between analytical and neural network model, which are hardly distinguishable. And also for problems like here, where we have a plate, again, a difference in the electric field through the height of the plate, which introduces together with a gravity load that acts upward, not downward, deformation upward directed, which is also combined then with instabilities that introduce wrinkling. And here again, also for two different kinds of strengths of the voltage of the electric field, we get very, very similar, hardly distinguishable results for these wrinkled patterns with the analytical model and with the neural network-based model. So in conclusion, we have very stable and accurate predictions when we use these polyconvex neural network models, even when we have large deformations and strains, when instabilities and post-buckling behavior occurs. Okay, so with this, I'd like to conclude my talk. So basically, I have introduced physics-enhanced machine learning concepts, which can be seen as physics-informed and physics-augmented machine learning, where the conclusion is that basically we want to introduce physical and mathematical structure as an inductive bias into the machine learning models. We have different ways to do it, and we see that it has a lot of benefits. And here we use this for material modeling and multiscale simulation, where we develop different models for hyperelasticity, where sometimes we are convex, sometimes we are not, where we have different approaches using invariance or using the deformation gradient-based model. We showed that these models can be used in nonlinear multiscale simulation for the mechanical case. We extended this to parametric dependencies for parametrized microstructures. And we also extended it to electroelasticity, where we now also have some very nice nonlinear finite element simulations that use these models. So what we are currently working on is using this in practical applications, also for different kinds of materials. We are working on the extension to inelastic material behavior, and specifically viscoelasticity. Other combinations of multiphysics, so include magnetic or thermal behavior. We're also working on implementations of this for dynamics and the inclusion of uncertainties in the microstructure or in the material behavior. And generally, a question that always exists in these cases is basically, what kind of data do you need? How much data do you need? How is this connected to the network structures that you are using and the types of neural networks that you're using, and then also the generalization capabilities that you can observe. So with this, I'd like to thank you for your attention. Thank you for the invitation to give this presentation again. And if you're interested in our work, feel free to check out our website or approach me. We are always happy to collaborate or host visitors and so on. Thank you. Okay, I'm happy to answer any questions if they are, if you have some.
Can you hear us?
Now, yes.
Well done, Oliver, and thanks so much for sharing your work. It was also personally nice to see what you over the last few years. I really did enjoy it a lot, and I don't think we've had questions on solid mechanics before, so I think it's quite a nice kind of like nice to have also. So we do have a question from Christian, who has nicely written it. in the chat box. I will read it to you. So he says, you used perturbation theory to provide some approximate solutions for the nonlinear effects in your framework. Can you please elaborate?
Yes. So basically, we used in the very beginning, let me go there. Almost there. Yeah, here. So basically for the homogenization of the microstructural behavior for which we use beam elements here, we have, especially in compression of the microstructure, we can have instabilities where the simulation would not converge if you do not apply some perturbation and basically influence in which direction the simulation will go at the point of the instability. But these instabilities, they are basically very reproducible, I would say. So independent of like how much perturbation you introduce, you will always get the same, more or less the same macroscopic response. And here we actually compare different approaches, like we did an eigenmode analysis and then applied the buckling modes as perturbations, but we also tried just using random perturbations. And in both cases, we get very similar results. And for the training data, basically, this is shown what is, or this is shown in this curve. We could use the mean, or we always use now the mean as an input, the mean of all these perturbed simulations as an input for training the neural network. But we could actually also use all the simulations that we did and then also investigate the influence of these uncertainties on the macroscopic response or on the neural network model.
Yeah, thanks, because I missed this part, sorry, because of the slide, the check. And
yes.
there's also a second, I will just, Zach, I will just read it myself. So the second question, I really like the formalism and the overall framework you actually put on, and like how you guided us thoroughly to each step and assessing the condition, this invariance, the objectivity, and so on. But like, this seems to me that you already have a recipe to formulate this in also other contexts where we have micro-macro interactions. For example, the fields I mentioned at the beginning, for example, traffic optimization and or, for example, cellular interactions in cancer growth. There we also have interesting physical and chemical processes. And do you already prepare a paper where you actually give a more thorough like recipe for people to actually pick it up and apply it to their field?
No, I think there are two reasons why we don't have that. The first is that we don't know so much about the other fields. The second, which is the bigger problem, in my opinion, is that I'm not sure whether there is actually such a recipe, because it really depends on what kind of conditions you have. And basically, if you have a generator that allows you to augment your model with this physical property. So for instance, we have here the material frame indifference and the material symmetry, which are kind of very similar conditions that this has to be valid for applying a rotation matrix, either when you apply it from the left or from the right to the deformation gradient. But the consequences of this can be very different and can be very, the ways to implement it can be very different. So basically, like here you see the invariance, and this definition of the invariance, these are the isotropic invariance. They ensure automatically the objectivity, because basically you always have F transpose F inside somewhere, and this cancels out the Q transpose Q, and this gives you objectivity. But for the material symmetry, where you apply the F, the Q or the rotation on the other side, such an approach is not so easily possible. And there you need, if you define invariance, you cannot work with the members of the material symmetry group, the G here, but you have to work actually with structural tensors that are used to generate the symmetry group. So you have to take different approaches for these two conditions, though they look very similar. And then also, like I said, this symmetrization operation, it works or is exact if you have a finite material symmetry group, but if you have an infinite material symmetry group, the sum is always going to be a discrete operation. So you have to make a choice of certain finite subgroup of the infinite symmetry group, or you have to think again of other ways. So it's very difficult to come up really with a recipe. You have to look at what kind of condition you have and then see how you can implement that.
Yeah.
Thank you, Christian.
Okay, I see further questions in the chat.
Yes. We have a question from Val. How hard is it to extend with Ogden material model where you are not dealing with invariants, but with principal stretches?
Yes, so basically with the principal stretches, if I'm not wrong, you cannot ensure, for instance, the polyconvexity directly. But of course, you could formulate a material model in terms of principal stretches, where you take the principal stretches as an input, which will fulfill the objectivity condition because they are computed from the right Cauchy-Green tensor. But I'm also not sure how this could be extended into other kinds of material symmetries, because this would apply only to isotropic materials, but to anisotropic materials, I'm not sure how the Ogden model is extended or generalized. So, I mean, the idea here is not that you use an Ogden model or a Mooney-Rivlin model or whatever. The idea here is that you can formulate a model using a neural network, which can take invariants or can take the deformation gradient as an input.
Thank you.
Thank you, Val. So if you have time, Oliver, it's up to you. We have from Zorden. Hello, Zorden. Good to see you.
Hi, Zach.
So, do you like to ask a person?
Yeah, I mean, like, if I can ask the question on my own, that would be great. Yeah, thanks, Oliver, for the presentation. I used to work at the SUTD as well, just like you.
Wow.
So, yeah, so I'm interested in this idea, and I'm curious if these pins or pens can actually help with simulating natural materials, because then with natural materials, usually homogenization, it doesn't really help. It causes a lot of inaccuracy. So we need to integrate, of course, some experiment data. Does your workflow also work for integrating experiment data from physical samples, for example? Yeah.
Yes, certainly. So this is basically what I meant in the very end when I said we are looking into applications. We are also looking into applications where you just use experimental data to train the models. Thank you for the question, because I should have mentioned this earlier, like where the data comes from, it doesn't matter in this case. So it can be from homogenization, but it can also be from experiments. And like I say here, especially the convexity adds a lot of structure to the model, which means that you can calibrate actually with very little data. Like here, we only use uniaxial tension and share homogenized data, but this could also come from experiments and train the model on it. And we still get a very good prediction also in these unseen test cases, which are much more complicated. So if you have experimental data for such a natural material, I'd be happy to try if we can fit the models to this data.
Yeah, sure. I mean, like, we're working on some sort of like self-shaping wood composites, actually. So yeah, I would get in touch, and then maybe we can collaborate something. Great.
Yeah,
thanks.
Fantastic. Oh, we have another question. No, okay. Are there any other questions? You have a question? Very good.
If you don't mind, I do have a question. I'm particularly interested in this physics augmented approach. So for the physics informed approach, basically the PDA residuals and the boundary conditions are effectively imposed in a weak form, as you said, in the loss function, yeah? it's not quite clear to me where especially the boundary conditions, and yeah, if you want also the PDE residuals, I mean, or what's the loss function in this physics augmented approach, and
Yeah.
where do you boundary conditions?
Yeah, I mean, so in this case, we are not solving PDE with our neural network. We are just expressing the material model. So I just use this as an example over here. But basically, this also relates to Christian's question. Basically, if you're trying to formulate or I would say formulating a physics-informed model is rather simple in the sense that it's in many cases you have this discriminator or you have this residual and you can just add it to the loss function and this will inform the model. Formulating a physics augmented model is much harder because basically you have to have a lot more knowledge about the problem in order to know what the possible generator is and how you apply this to the model. So for instance, this symmetrization operation over here that we use as a generator for the correct material symmetry, this is something that has not been used before in analytical models, because in analytical models, this wouldn't make any sense. So you would have an analytical expression over here as this W0, but then you still apply a complicated sum around it. So this is something not very handy. So one would not do this in an analytical model. So this is not an approach that would be, that would have been used before for this application. But since you're using here you're in a numerical environment with the neural network model, so you can easily do this, and since you have no direct understanding or no direct interpretation of the model structure, it makes more sense to do it. But this is basically this kind of generator that you have to come up with in order to fulfill certain physical requirements. So the idea behind these generators is basically that you do not need a discriminator, you do not have any residual or any loss, basically, because using this generator, you make sure that your physical requirement is fulfilled in a hard way. So the easier example is maybe the usage of C here, because like we want the objectivity, and the objectivity means that the W of F is equal to W of QF over here. And now if we have F transpose F, and you replace F with QF, then basically you get F transpose Q transpose Q F. And now, since these are rotation matrices, this is the identity. So you get F transpose F, which means F W of QF is equal to W of F if you use C as an input. So this C automatically is a generator of the objectivity condition, or of a function that fulfills the objectivity condition. I hope this answers your question.
Yeah,
okay, now I can hear you okay.
See, where do you precisely impose the boundary conditions? Or
there are no boundary conditions here because we're not solving a partial differential equation. So we are basically determining a material model in terms of a strain energy function, which is there to basically just fit this data. There's no boundary value problem here. We're not solving a PDE. I mean, we are solving a PDE then in the end when we are doing the finite element simulation over here. So maybe I can show this slide. So basically here we are solving a PDE where this P of F is computed using a neural network. And here the finite element method is used to solve the PDE. And no PIN or other neural network machine learning based method. The neural network or the machine learning just enters here in the material model.
okay, I see now. Okay. Thank you.
Okay.
You're welcome.
Oliver, we don't want to keep you any longer, but thank you so
It's
much
okay.
for. And I hope that you can follow on in the future seminars. We have a few coming up.
Yes, I'm checking the invites and I tune in when there's something interesting. And I also forwarded the invite to my students, so if they're interested in the topic, they will also attend.
Fantastic, thank you so much. I say thank you to everyone for joining as always. And yeah, I'm Singer, Mr. Christian. Thank you to for joining. All right.
Okay, see you.
Have a good one.
Bye.
Thank you.